Hello, and welcome to the third and final lecture on vectors. In the previous lectures, we discussed how to add vectors, how to break them up into components, and also two of the three ways that you can multiply vectors together. Today, I'd like to discuss the third and final way that you can multiply vectors, and that's called the vector product. We also know it as the cross product. Now, as a refresher, previously we talked about scalar multiplication. And as a reminder, when you multiply vectors by a scalar, what you do is you potentially scale the length of the vector or flip it 180 degrees. We also talked about the dot product. When you take the dot product between two vectors, and remember it's a reversible process, A dot B is equal to B dot A. One way of visualizing it is that it gives you the length of one vector along another vector. The cross product is a little more complicated than that. Scalar multiplication, when you're done with it, gives you a vector. The dot product, when you're done with it, gives you a scalar. The cross product, when you're done with it, gives you a vector, but that vector is unlike the other two vectors. The way it works is like this. So I want you to imagine two vectors. We'll call them vectors A and B. The act of taking the cross product, A cross B, gives you a third vector. Which we'll call C. And that vector has the following properties. It is at right angles to A and also at right angles to B. Now, technical terminology for being at right angles is called being orthogonal. So the act of crossing A into B gives you an orthogonal vector that points away from them, and in this case is vector C. Now, one of the things that makes the cross product a little bit difficult to handle is the way you actually carry the cross product out. We're going to discuss two of the three ways of doing cross products. The third way you'll get in a more advanced class. That said, mathematically, I want you to consider two vectors. And to do that, let's draw a coordinate system. Now, doing cross products requires a three-dimensional coordinate system because of the fact that you have that orthogonal vector that's created. So what I'm going to do here is to create one. We're used to these. This is the z direction, this is the y direction, and this is the x direction. Now, so I want you to consider, like I said before, two vectors. Vector A, which I'll say points 5 meters in the x direction and 3 meters in the y direction. And vector B, which points 6 meters in the x direction and 4 meters in the z direction. Now, let's draw these. 1, 2, 4, 5 is about here. 1, 2, 3 is about here. So vector A would point to about here in the xy plane. Vector B is 6 along x. 1, 2, 3, 4, 5, 6 approximately. And 4 of z. 1, 2, 3, 4. So it's going to point approximately from here to about here. So let's label these. Vector A and vector B. Now, so visually this is what we have. So let's talk about the determinant method for doing the cross product between these two vectors. Now you may have seen determinants before, perhaps in advanced algebra or in trigonometry. I'll give you a refresher as we do this. So what we would like to do is to perform the following cross product, A cross B. Now, let me draw my determinant. In the top part, the top row of the determinant, we'll put x hat, y hat, and z hat. These will form the columns for when I actually carry this operation out. So, A is 5 meters along the x direction. You put it in that column. 3 meters in the y direction, and has no z component. B is 6 meters in the x direction. It has no y component, but it is 4 meters in the z direction. So, here's how we carry this out. To start with, you put your finger over x and you block out the row and the column that x is in. So we'll use these lines right here to do that. This blocks out that column and that row. The next thing you do is to write down x hat. Oops. Now, the rules are, looking at this square right here, upper left times lower right minus lower left times upper right. 3 meters times 4 meters minus 0 times 0. 3 times 4 is 12. Meters squared minus 0 times 0. The next thing we're going to do is to look at the y part. Now, let's block those out. If you put your finger over y, you block its column and its row. For the second one, for y, you put a minus sign and put y hat. The square that we're looking at is this square right here, but with these eliminated. So, upper left times lower right minus lower left times upper right. 5 times 4 is 20. meters times 0. Now, the third and final operation you do here involves z. Put your finger over z and block out its row and column. You add z, and again, upper left times lower right minus lower left times upper right. Six times 3 is 18. If we look at this and look at where the zeros are operating, here does not contribute, this does not contribute, and this does not contribute. The vector that we have is 12 meters squared in the x-hat direction minus 20 meters squared in the y-hat direction minus 18 meters squared in the z-hat direction. So were we to draw A cross B, it would be way down the x-axis, way down the minus y-axis, and way down the z-axis, giving us a vector that would point approximately in this direction right here. This right here would be A cross B. Now, cross products are typically used whenever you're dealing with concepts like torque, concepts like the magnetic field. And more complicated concepts, if you've had Calculus 3, like the curl. Now, this is one method of calculating a cross product. Another method involves looking at the magnitude of the vectors that are involved and using something called the right-hand rule. This is the right-hand rule. If you know the direction that A points and you know the direction that B points, if you were to put your pointer finger in the direction of A and your middle finger in the direction of B, your thumb will give you the direction of A cross B, as long as you stretch them out and make nice right angles to each other. Another way that you can do the cross product is to take and put your fingers, all four fingers, not your thumb, in the direction of A. Let your palm sit in the direction of B. And as you close your fingers to make a fist, the direction of your thumb gives you A cross B as well. Now, unlike the dot product and unlike the scalar product, the cross product is a little bit more complicated in that, as I pointed out earlier, A dot B is the same thing as B dot A. If you take a number, a scalar, and multiply it by vector A, that's the same thing as the vector times that number. Unfortunately, with the cross product, A cross B is not the same thing as B cross A. They're actually associated to each other via negatives. So A cross B is equal to minus B cross A. And that's the reason why, if you look at the right-hand rule, in the bottom right here, you see that B cross A is equal to minus A cross B. Now, let's do an example dealing with the right-hand rule. We'll draw another coordinate system. z, y, and x again. And this time, the vectors that I'd like to use, I'd like to place them in the xy plane just to make life easy. Whoops. I thought I'd selected that. I guess not. So we'll call this A. And we'll call this B. Now, here, the angle between vectors A and B we'll call theta, much like the dot product. Now here, just as an example, I'm going to let theta equal to 35 degrees. The magnitude of A, 20 meters. The magnitude of B, 15 meters. And what I'd like to do is to find A cross B. Actually, this is a mistake. I don't want to mislead you guys. So, the magnitude without the vector hat. 15 meters, I believe. Yes. So, before we do anything, let's see if we can figure out the direction. So, we would like to calculate A cross B. Using the right-hand rule, put your pointer finger in the direction of A and your middle finger in the direction of B. Your thumb will tell you the direction of A cross B. If you do that, you end up with a vector that points down. Straight down, in this case, the z-axis. It's going to be somewhere in this direction, like this. So we have the direction, but what we're missing is the magnitude, because remember, magnitudes, or vectors rather, have magnitudes and directions. So the version of the cross product that I would like to use here looks like this. It's the magnitude of A times the magnitude of B times sine of theta. Now this should look very familiar. This looks a lot like what A dot B would be, with the exception of the fact that you have a sine here instead of a cosine. So, to carry this operation out, to figure out the magnitude of A cross B, all you do is look at the lengths. 20 meters times 15 meters times sine of 35 degrees. Now, if you perform this calculation, which I'll do now, 20 times 15 times sine of 35 you get 172 meters squared. So this thing is incredibly long, points way down there, but that's direction using the right-hand rule. So, to summarize, there are two basic ways that you can take the cross product. You can use a determinant to figure out the actual components and their lengths, or you can use the right-hand rule. Which way depends upon the simplicity of the problem that you're working. If your vectors lie within one of the planes, for example, both of them lie within the xy plane, the zy plane, or the zx plane, using this particular version and the right-hand rule is definitely the way to go. If you have vectors that are more complicated, for example, these two right here, which have components that don't explicitly lie within a plane, then you probably need to use the determinant.